Okay, very good. So welcome to lecture 3 on dark matter. So what I want to do today, I'll first say just a couple of last things about what we talked about yesterday, which was the example of thermal dark matter. And I want to just say a little bit about examples in which this scenario comes up, because this is the classic WIMP or weakly interacting massive particle scenario that has driven a lot of the experimental effort to find dark matter over the last several decades. Then I want to go on and talk about another example from the other end of the mass range that we talked about yesterday, which is the case of ultralight cold dark matter. In particular, I want to talk about the example of Accin dark matter, which is motivated by the strong CP problem. Now, this is going to be really an outline of the cosmology of Accin dark matter and the searches for Accin dark matter and the motivations for Accin dark matter, because each of those topics, if I wanted to focus on it, could be at least a whole lecture on its own or more. Okay, so if you want more detail on that, let me know, and I can point you to the TASI lectures where people did give 3 or 4 lectures purely on Accin dark matter. Then, after we talk about the cosmology of Accin dark matter, why an ultralight field that you might think would be relativistic in the present day can act like cold dark matter, I want to talk a little bit about how we might look for it. So move from the ideas for what dark matter could be to how might we probe it experimentally. And then I want to, in the second half of this lecture hopefully, I want to talk about going back to this thermal picture. If we know that dark matter's abundance is controlled by its interaction with the standard model, that gives us some very clean benchmarks to aim for. And I want to talk about traditional dark matter direct detection experiments, how they work, what kind of signal you might look for. All right, but so to begin with, let's just summarize again what we said last time, since I was confused about the time allowed for the lecture, and thus the end of last time was a little bit mixed up. So last time we talked about the thermal freeze-out scenario, where dark matter is originally in thermal contact with the standard model through annihilation type reactions, through and then those number changing interactions freeze out, leaving a relic abundance of dark matter. So in this case, the abundance is controlled by the interactions between the dark matter and the standard model, which is wonderful for phenomenologists and experimentalists because the presence of those interactions is something that we can look for in other channels. We argued that this works, that this basic idea can work for roughly keV to 100 TeV mass dm. This lower limit comes from bounds on the dark matter being too warm. This upper limit comes from the fact that if the annihilation rate is what's controlling the abundance, you need the annihilation rate to have a certain value, which we worked out last time corresponded to a cross-section sigma v of 1 over mass squared, where the mass was about 100 TeV. So if your mass is appreciable, so to make this a little bit more formal, there's a unitarity bound on the annihilation rate, which says basically that sigma, the dissipative annihilation cross-section, should be constrained by this geometric cross-section 4 pi over k squared. So k here is the momentum of the particle. It turns out that if you do a careful calculation of this, then the unitarity bound constrains the maximum annihilation cross-section. As you go up higher in mass, this maximum annihilation cross-section gets smaller. If your mass is greater than a few hundred TeV, then sigma is too low to get the right to get the right abundance. Now, that doesn't mean it's completely impossible for the dark matter to be heavier than 100 TeV. If the dark matter that we talk about today is actually a composite particle made from a bound state of many, many, many lighter particles, then this limit is not going to apply. because you can annihilate the way the lighter particles with a large annihilation cross-section, and then later they can form dark matter. Similarly, if you're talking about something like primordial black holes, this is not what sets their abundance. This constraint doesn't apply. But if you want point-like dark matter particles whose abundance is determined by thermal freeze-out, then it pushes you into this wide but well-defined mass range. So now let's talk about the other part of the mass range so this has guided a lot of the thinking on how to search for particle dark matter the last few decades. But there's a completely different region, which we talked about last time. Actually, sorry. Before I go on and talk about ultralight cold dark matter, I'll say one more thing about this. So this is a general mechanism, works for a huge range of possibilities. There's a specific subregion in this that has gotten a lot of particular attention, which is the classic WIMP, which corresponds to a weak scale, interactions, and weak scale masses. This is one way to satisfy, to get the right cross-section. It's not the only way. And in particular, the very classic WIMP, it has a weak scale interaction because the interaction is actually mediated by the W and Z. Or the Higgs, which is at a similar mass scale. Now, this comes up in the example of the lightest neutralino in supersymmetric models. So in supersymmetry, every particle in the standard model has a counterpart partner particle. The superpartners carry odd R parity, whereas standard model particles carry even R parity. This is required to ensure that allowing supersymmetry doesn't make the proton decay. So in SUSY, there is a lightest superpartner particle, a lightest particle with R parity odd. So the lightest superpartner is stable because R parity is conserved. If you've got something with R parity odd, it can't decay into purely R parity even particles. So a generic feature of supersymmetric theories is that lightest superpartner is stable, and often the lightest superpartner is what's called a neutralino, so that's a superpartner of the gauge bosons of the standard model. So if the lightest supersymmetric particle, the LSP, so a common situation is the LSP neutralino can be a good thermal DM candidate. So neutralino here means fermionic superpartner of the W boson sorry? Well, I can break the chalk, but well, it means writing with a very short piece of chalk, which is, yeah, to WZ, the Higgs boson. Well, yeah, okay, said another way. The superpartners to the SU2 gauge bosons. And the, well, yeah, I'll just say the Z. It's close enough. So in this case, so you can work this out explicitly. It turns out that if you just look at the simple cases where your lightest neutralino is the superpartner of the W, so it's a nearly pure, it's called a WENO, W-ENO, or is this the superpartner of the Higgs, which is the Higgs-ENO, those are both still good dark matter candidates that haven't been ruled out by experimental observations. So, for example, so if you look at the pure we know dark matter that is the superpartner of the W, and you work out the thermal freeze-out calculation that we did last time in detail, it's a little bit more complicated because in a SUSY theory, you don't just have the dark matter and the standard model, you've got a lot of other particles which you may need to take into account in this calculation. So when you work it out, you do this calculation, you find that it has the correct relic density for masses around 3 TeV. So this is, similar to, as I said last time, if you just took like alpha around an electroweak alpha, then you guess it was a mass scale for the dark matter of about 100 TeV divided by alpha, so that's about 3 TeV. The pure Higgs-Xeno, so this is what it sounds like. The superpartner of the Higgs. If your lightest supersymmetric particle is a nearly pure Higgs-Xeno, then that's also a good dark matter candidate, and it gets the correct relic density through this thermal freeze-out process, just exactly what we calculated last time at a mass of about 1 TeV. So if you have supersymmetry, and if the bottom of the spectrum of superpartners, if the lightest superpartner is sort of around this TeV scale, then you can naturally obtain, there are other reasons for supersymmetry, which I'm not going to go into in depth because that's another topic that can take many lectures, but, or all the details of SUSY, but supersymmetry is potentially implicated in coming to a resolution of the hierarchy problem. It helps unify gauge couplings in the standard model. There are lots of other reasons for it. Almost coincidentally, if you have supersymmetry at the weak scale, or an order of magnitude or so above the weak scale, then you can pretty naturally get the right dark matter abundance. Now, this scenario has been, so the very optimistic scenario 10 years ago was that supersymmetry was going to be there, the bottom of the spectrum was going to be at like 100 GeV, the LHC was going to switch on, and we were going to find all these supersymmetric particles and also solve the dark matter problem. Now, this did not happen. This was the sales pitch that I got when I started grad school in 2006, but that didn't pan out. But there are a couple of things. First off, these very simple scenarios like 1 or 3 TeV dark matter, they're not yet really being tested by the LHC. If you have pure we know or pure Higgs-Xeno dark matter, it would be very hard to find it at colliders. If the bottom of your SUSY mass scale is that high, then solving naturalness problems is a bit harder, but there are still other advantages of supersymmetry. So sometimes, 10 years ago people were like, oh, this is clearly the answer. This is just going to be it. We're going to turn on the LHC. We're going to find everything. That clearly didn't happen, but I think sometimes there is a little bit too much pushback. This is a personal opinion, not. So I think sometimes there is a little too much pushback on that. There's actually still, it could still be true that SUSY is out there and the simple SUSY WIMP scenario is the right answer. It's just at a somewhat higher mass scale than 100 GeV. But beyond this SUSY WIMP scenario, this was the motivation for a lot of the searches for dark matter and a lot of work I'm talking about. But the basic mechanism for getting the right dark matter abundance that we talked about last time works perfectly fine for any mass scales between about keV and 100 TeV. Okay, that's what I wanted to say about WIMPs freeze out. Are there any questions before I go on and talk about the other classic example of dark matter as a cold ultralight field? Yeah? Sorry, which one? So there's we maybe. So the thing is, the direct detection cross-section comes about. So like the tree level direct detection cross-section for the Higgs-Xeno comes about through like Higgs-Xeno-Bino mixing. So you need a, so at least, I mean, we could talk about this more, but at least this is how I understand it. So, I mean, if you've got a nearly pure Higgs XENO that has a small Beano fraction, then there's a tree-level diagram that involves Higgs exchange, and you're just done. You're right. It's very ruled out. But if you were really looking at pure Higgs XENO with no mixing with the gauge XENOs at all, then that vertex is zero. That vertex is zero. That vertex is suppressed. So there's a paper by Hill and Solon from a few years ago. So then you can work out. So the cross section for the Higgs XENO then proceeds through a loop diagram involving W. Well, at one loop it involves how does it go? Yeah, it proceeds, I believe, through a loop diagram involving gauge boson exchanges. Now, you can estimate the size of that and look at the size of that, and that also looks like it should be ruled out. Like, not by a huge margin, like the tree-level diagram, but still ruled out. But it turns out that there's a cancellation which involves two loop diagrams as well as one loop diagrams, which Hill and Solon worked out in like 2013 or 2014. And that cancellation depends sensitively on the mass of the Higgs boson, but like for 125 GeV Higgs boson, which is what we appear to have, the cancellation is really strong. So as a consequence, that Higgs XENO scenario is actually not really tested by direct detection. It's just a coincidence. It's just that you have a cancellation between different diagrams. But I think often when people say the Higgs XENO is ruled out, they're thinking in the context of you don't need a very big mixing with the Beano in order to have a really big cross section. But you do need. I mean, but it depends on the Higgs XENO Beano mixing. So let's talk about this more offline, and I can show you the results that I'm looking at. Because I mean it matters that there's a sorry, go on. Let's talk about it offline. Okay. So having said this about why we might be interested in the thermal WIMP scenario, it's predictive, it gives you an indication of the couplings between dark matter and the standard model. There are lots of ways to search for it, as we'll talk about later this week, and it has motivations in that the sort of classic example of this is the SUSY neutralino. Let's talk about the other end of the spectrum and talk about ultralight, cold, non-thermal, dark matter. And in particular, let's talk about this from the example of Accin dark matter. So, actually, I will make one more last comment on this. One is that it comes up in the case of SUSY, but where I said there can be other particles that are involved in freeze-out, not just the dark matter. More generally, there can be lots of variations on the scenario that I showed you last time. You can have cases where the cross-section has some dependence on the temperature or velocity as well. You can have cases where there's more than one species involved. You can have cases where the dark matter is annihilating into some other dark sector particles, which then later decay back to the standard model, or maybe don't. You can have cases where it's not a two-body process that dominates the annihilation, but a three-body process. This is the case for SIMPs, strongly interacting dark matter, which have been studied quite a bit in the last few years. You can have cases where it's not the annihilation which really dominates the freeze-out, but where scattering between dark matter and the standard model decouples before the annihilation does. And so there's still an interaction with the standard model, which is important in the early history of the universe, but it's an elastic scattering cross-section rather than annihilation cross-section. You can have scenarios like freeze-in, where the dark matter and the standard model never quite get to thermal equilibrium, but they approach it over cosmic time. Then again, it's an interaction between the standard model and the dark matter that determines how much dark matter you have, but in the sense of as you turn up the interaction, more dark matter gets produced, as opposed to this case, where as you turn up the interaction, the dark matter gets depleted. So there are a lot of variations on this story. What I've given you is the sort of simple picture from which these modified scenarios tend to build off. Okay, but now, belatedly, to axions. So here let me do the opposite to what I did with the SUSY WIMPs, which instead of starting with the cosmology is to say, okay, let's start with the motivation in this case. So the motivation for axions is what's called the strong CP problem, which I will, again, outline briefly. If you want more detail, there's a good set of TASI lectures on the strong CP problem. Okay, so the basic strong CP problem is that in principle, the standard model Lagrangian could have a CP violating term in the QCD sector of the standard model, where this is the gluon field strength, this theta is just a parameter. So this is like the kinetic term for a field, except instead of it's effectively E dot B. It's CP violating. If CP is preserved, it will forbid this term, but we know that there is CP violation observationally in the quark sector of the standard model. And so there's no particular reason to expect this term to be 0. So you'd expect this. You'd expect this to be generated by CP violation in the quark sector. And from that, now this kind of term, the CP violating term, would induce an electric dipole moment for the neutron. You can work out the size of this neutron EDM from this kind of Lagrangian term. And my sources tell me you would expect this to be pretty small in terms of this theta parameter, in terms of like E times centimeters. This is like the charge, this is the length. You'd expect this to be like 5 times 10 to the minus 16. So that's a pretty small number. You might say, okay, this is fine, this seems totally reasonable. Except that the problem is that the experimental result is that this dipole moment is about 10 orders of magnitude smaller than this. So the parameter sitting in front of this expression, you say, okay, this theta, if this term in the Lagrangian is there, this coupling here has to be smaller than about 10 to the minus 10. So why so small? This is not a particularly, this doesn't look particularly natural. I mean, maybe it is just that way, but there's not sort of an obvious anthropic reason that if you had a neutron-electron dipole moment that was significantly larger than this, it would mess things up. I mean, this is a pretty small number anyway. So why so small? So this is the strong CP problem. There are various ideas for solutions to it. The one that we're going to talk about today is the Accin solution, which says, well, in order to get a dynamical reason that this is so small, let's suppose that instead of this being like just a fixed numerical parameter, this theta is actually some dynamical field, it's evolving in some potential, and the minimum of the potential is close to 0, or is at 0. So the field is just going to evolve naturally to a very small value. So this is so this is like an axion field, and we're putting in an effective cut. So FA is just a number, a mass scale. The effective coupling is 1 over. The one effective dimensional coupling is just. But then we need to explain why the VEV of A evolves toward a small value. So you can show, and I'm not going to go through the derivation because of time commitments, but they are in these notes if you want to take a look at them. You can derive an effective potential for this A field. I mean, we know this is coupled to this is coupled to QCD. This is coupled to the gluon sector. It's coupled to the quarks. And using, I believe, looking at the chiral limit of QCD is how you get this. You can show that there's this periodic potential for this field. I'm just asking you to take this on faith. I haven't demonstrated this. And again, if you want to look up the derivation, you can look it up yourself here. But this is not an uncommon setup when you're talking about very light dark matter, very light bosonic dark matter. You're going to be in a situation where you've got some scalar field, and you want to look at how does it evolve over time. So we'll show that in this particular case, for the axion, it evolves in such a way that the energy density stored in this field in A is going to behave like cold dark matter. Okay, so we can look at where the minima are so we can look at where the minima are in this potential. So we're going to get a minimum at A equals 0. This cos maximizes there at 1. So we're going to get a minimum of this potential. So this potential is periodic, and it has minima at A equals 2m pi. So, if we look at this as the value of A, we look at V of A, and we're going to have a potential that looks like this. Okay, so this is 0. This is minus 2 pi. This is plus 2 pi, and so on. Okay, so we know that we want this field. We want the expectation value of this field to float towards an extremely small value. So if we have a term like this in the Lagrangian. So let's suppose that we're somewhere in this region. So we're in this part of the potential. So if our field starts out here, it's going to roll towards this minimum at A equals 0. It will dynamically evolve towards the minimum of this potential. Okay, so let's consider So let's examine the potential around A equals 0. If we're close enough to the minimum, then we can expand this. So we're going to get just an offset term. And then we're going to get an A squared term. Now, I should say what are m pi and f pi that I've written down here. So these are basically just associated with the QCD scale. F pi is the pion decay constant. It's 93 MeV. M pi is the pion mass. It's 135 MeV. So whenever you see like f pi, m pi, it's basically the QC, it's, you know, up to factors of 2, it's basically the QCD scale squared. So from this potential, so we're going, if we have a term in our Lagrangian for this new field, we know that what terms involve this new field in our Lagrangian. Well, we know that it couples to the gluonic field strength, and it's going to have this potential term. So this piece here, if this is a scalar field, this is a mass term for this A field, for this axion. So from this potential, we can read off the axion mass. So first, we've got a potential which is parabolic about its minimum, which is the generic behavior, and its mass term is basically there's this combination of quark masses, which is just going to be an order 1 number. But so basically, the mass of this axion particle is just going to be related to its coupling. So the smaller we make it, the higher lighter we make it, the higher this scale Fa will be, and the more weakly it will couple to the standard model. So coupling, since the coupling goes like 1 over Fa. So we can put in the numerical values that I just put in here. We can put in estimates for the quark masses. So this is going to be something like 0. Let's just normalize. For reasons that will become obvious in a moment, I'm going to normalize this to a pretty high scale for Fa. So if I'm talking about so here I have a trade-off. If my mass of the axion was close to the QCD scale, my F for the axion would also be close to the QCD scale. The characteristic scale of my coupling would just be 1 over lambda QCD, and this would be like a QCD mass, QCD scale interactions field. But I have the freedom to make the coupling, the scale of the coupling extremely large, make the coupling extremely small, and that also pushes me to very low values of the axion mass. So why should I prefer one of these over the other? Why should I prefer the QCD axion to this ultralight axion? Well, the answer, of course, is that we haven't observationally seen the axion anywhere, except possibly in the strong CP problem. So we can set pretty strong constraints on heavier axions. And the other reason is that the light axion interacts so weakly that it was never in thermal contact with the standard model. And as a consequence, it can be a good candidate for ultralight, cold, dark matter. So let's see how this works out. So just summarize what so low MA is a small coupling. So we said earlier that if we want dark matter to be, this is nice from a dark matter perspective because we said earlier that if dark matter is lighter than about a keV, it can't possibly be in thermal contact with the standard model. But this gives us naturally, as we make the dark matter lighter, its coupling with the standard model is automatically going to get smaller and smaller. Okay, so if we wanted to look at this as a possible dark matter candidate, there are a few questions that we need to ask. We need to ask, were the axions ever in thermal equilibrium? With the standard model? and we want to ask, okay, and we also want to ask, are they stable? Or do they decay? If we're going to talk about milli-eV particles, they'd better be pretty out of thermal equilibrium with the standard model. I mean, a milli-eV is about the temperature of the universe today. So if they were in thermal contact with the standard model, they'd be pretty relativistic. We also want them to live for a long time. So you can estimate the time scale for the axion to decay into visible stuff. If they're this light, they can probably only decay into massless particles. So you can look at the time scale for decay to photons. And a parametric estimate of the time scale for decay to photons I'm going to make a bunch of statements without proof here, just to give you a picture of what is the available landscape for axions. It comes out as about for EV mass axions, the time scale for decay would be about 10 to the 24 seconds. So the age of the universe in seconds, we heard in the first day, 1 year in seconds is pi times 10 to the 7. The universe is about 10 to the 10 years old, so the age of the universe is about pi times 10 to the 17 seconds, or a little bit more than that. So this is 7 orders of magnitude longer than the age of the universe, so this is fine. But you see this scaling to the -5 with mass, so if you look at a 100 EV axion, the lifetime will be 10 orders of magnitude shorter, and that won't be a very good dark matter candidate anymore. So this tells us, this tells us that if you want dark matter axions to be dark matter, axion DM would have to have a mass scale less than about 20 eV, or it won't be too stable on time scales of the age of the universe. Now, you can also, this question about were they in thermal equilibrium, you have to do a little bit more work, but you can show that if the axions are heavier than about a milli eV, or 10 to the -3 times 10 to the -2 eV, then the axions can attain equilibrium with the standard model. They couple well enough to do that, and so in that case they act as a hot dark matter candidate. So what you find then is that if axions are about in this range, then they're a viable contributor to that 1% of dark matter that could be hot dark matter. So, and the fraction of axions over the fraction of dm is order. So you can, if you work this out for the case of hot dark matter, so above this scale, the axions are in thermal equilibrium. You can do exactly the calculation that we just did the other day, yesterday, yes, not that long ago, and you can show that. So you can show that if you've got axions sort of in this light mass range, they're not cold dark matter, but they could be a subdominant component of hot dark matter. So if we're going to look for axions that are 100% of dark matter, we need to be down at this scale, 10 to the -3 eV or lighter, which tells you from this expression, it's about the milli eV scale I wrote down here, not by coincidence, that tells us that we're talking about whatever physics governs, its coupling to the standard model is at some pretty high scale, about 10 to the 10 GeV or heavier. We need this is for the QCD axion. If you play with particles that are light scalar fields, but not the QCD axion, then you can, and have a different relationship between the coupling and the mass, then you could potentially make the mass a bit higher if the coupling's smaller. Okay, so let's look at the case of this thermal axion, of this non-thermal axion. So what we're imagining here is that early in the universe, these axions were produced. They evolved in the potential that I wrote down earlier. This axion field evolves. It doesn't have any interactions with the standard model. It's just evolving like the scalar fields that you talked about in slow roll inflation. Those scalar fields are evolving in some potential. You don't care about what interactions they have with the other particles that we know about, if there even are any particles like that. So we're going to do an analysis that is basically like the analysis of slow roll inflation, just asking, let's consider the expectation value of this axion field as a classical scalar field evolving in the early universe. Yeah? So this is assuming that axions were in thermal equilibrium with the standard model, so their abundance was controlled. So standard model particles scattering off each other made a whole bunch of axions. Then they decoupled while they were relativistic and used the hot dark matter calculation that we did yesterday. So then the number density of axions is going to be like somewhat comparable to that of photons within a couple of orders of magnitude. So then you just take that number density, multiply by their mass, and ask, okay, what's that abundance? So yes, in that case, if you had 10 to the minus 3 eV axions, if you have anything in the universe that has the same number density as photons, but its mass is like 10 to the minus 4 or 10 to the minus 5 eV, it's not going to contribute much to the total mass budget. Like, that's true. But, so this is only true for thermal axions. Right, so what we're going to posit now is that the abundance of axions did not come about by being produced by interactions of standard model particles. It was just an initial condition. There were some axions around in the early universe, was set by some initial condition, and we'll understand how that affects the final mass and what the possible range for the initial condition is. Yeah, so what's that initial condition? So let me draw again the potential that I drew before, zoomed in on this region around the minimum. So the picture that we're going to have here is that the axion field, the expectation of the axion field, so we're going to consider a classical field, which is the expectation value of this axion field, and I want to know how this field evolves in time and how the energy density stored in this field evolves in time. So here's the value of my axion field. Here's the potential associated with my axion field. The picture here is that early in the universe, for a reason that I don't understand, there was an initial condition that placed this. So before whatever physics gave rise to the axion, which could be a Pichy-Quinn mechanism, whatever physics gave rise to the axion, presumably this potential wasn't around. Then we passed the scale where the temperature of the universe cooled below the scale where that physics was important. This potential was developed, and the initial value of the field was somewhere located away from zero. So we call this the misalignment. We say there was some initial misalignment between the initial value of this field and its potential. And then we want to understand, well, okay, this is going to roll in this potential, just like the inflaton rolls in its inflationary potential. We want to understand how the evolution of this field behaves and what happens to the energy density stored in this field. Okay, so the equation of motion for this classical scalar field is, as well, I guess I've erased it, but we can write this axion potential close to its minimum as being a constant offset plus a term that is like a half ma squared theta squared. Okay, I mean, like this was just how we defined ma, that we said this term in the Lagrangian is a scalar mass term, so close to the minimum. Close to the minimum, we can just approximate the potential like this. So that tells us that our equations of motion are the equations of motion for a scalar field in an expanding universe. So we have these two terms which describe the redshifting of the field, and then a term which comes from the derivative of the potential. This is So we're going to take this equation of motion with this initial condition, and we're going to understand how the field behaves under it. All right, so as with the thermal freeze-out, it's helpful to think about two different regimes here. So I mean, this is just telling you that the rolling of the field is governed by the derivative of the potential, by the slope of the potential. So, first regime, where we can neglect the this last term. Well, in that case, if we can neglect that last term, then a valid solution to this is just that the field doesn't change. It's just that its derivative is 0. So it just stays fixed at its initial value for all time. So this gives us, so the scalar field, we say that it's frozen. At an initial value. Which I'm going to call this. All right, so early in the universe, h is it's extremely large. H is an inverse time scale. Axion is like a milli-eV, so in the radiation-dominated epoch, this is like t squared over m Planck. So in the early universe, this field just isn't going to evolve. You start it at this point, it just stays fixed at this point, this value of theta, it doesn't roll. So when this will change, when we can no longer neglect this term compared to this term, which happens around where MA becomes comparable to H. Now, see why I say oscillate? Well, if I could completely ignore this middle term, this H term, if I were to just totally ignore the Hubble expansion, then we know how to solve this differential equation, right? Like this is just a this is just a simple oscillator. So if the H term was neglected, we would say that this would scale like cos or sine of MAT. Let's say. So as t goes to 0, we want this to go to its initial value, so we would just have this solution. Now, we can't really fully neglect the H term. There's going to be this fast oscillation as a result of these two terms, but there's also going to be a slow variation of this field. So this field is at this point sloshing around in this potential, oscillating back and forward. But this term is going to give us what we call Hubble friction, which is that over time, this oscillation is going to get more pronounced and it's going to converge towards the minimum of this potential. So a better ansatz is that the field is going to scale as the initial condition times this oscillatory piece plus a slowly varying function that is being driven by the Hubble friction. And what you can show, if you look at the evolution of this equation. I'm happy to talk through it with anyone who's interested, but what you show from this is that the evolution of f of t turns out to be proportional to the scale factor to the -3/2. The easiest way that I know to see that is if you multiply this cross-section by theta dot, then you can rewrite it like, I mean, this is just multiplying the whole equation by theta dot, but then we can write this and then, because we're primarily interested here not in these fast oscillations cos m8 described by this factor, but by this slow evolution, if we take the expectation value of this result, then we can get a simple equation for how the expectation value of this quantity changes over time. Now, I told you that I wanted to understand how the energy density in this field evolved over time. So what's the energy density due to a scalar field evolving in a potential? So the energy density stored in this field is, so there's a potential energy term plus a kinetic energy term. The potential energy term is just given by V. So this is the value for V of phi, and then there's a effective kinetic energy term which looks like this. Now, if with this ansatz, we can expand this out. This first term is going to give us a cos squared term. The second term, since it's a time derivative of this, is going to give us a sine squared term. So even though the field itself may be sloshing back and forward in this potential very rapidly, the total energy stored in the field is only evolving slowly with time. We can write this as just the expectation value of, just in terms of the expectation value of the square of this derivative. We could also have written it in terms, if we wanted, of the expectation value of the field itself, because to the degree that we can drop the the derivatives with f, this is also just approximately equal to This is also just so this is just saying that yeah, I mean this quantity, if we square this, we'll just get theta naught squared, f squared, cos squared, take the expectation value of cos squared over many oscillations, and you're just going to get a half. Actually, so maybe I don't need a half there. Yeah, I think actually I don't need a half there, because the half comes from the expectation value of the cos squared theta, or the expectation value of the sine squared theta. So if what I care about is the evolution of these slowly varying quantities, which tell me about the total energy density content of the field, then what I'll find what I'll find if I take the expectation value of this equation is that this term and this term, these are both just telling me about the energy density of the field. So these two terms add together and just give me d by dt of rho in the field. Yeah, okay, no, sorry, I got to be a little bit careful there. Yeah, these two terms add together give me, those two terms adding together are going to give me just a half rho plus a half rho. This is just going to give me 3h rho. So this is the same equation that we saw previously in just the evolution for a dark matter species that didn't have any number changing interactions. This just corresponds to the energy density of the field being proportional to a to the minus 3. So here we have something that cosmologically behaves like cold collisionless matter. Even though we're not talking about individual matter particles here, we're talking about a classical scalar field which pervades the whole universe. And the actual value of that scalar field is oscillating forward madly at any point in time, but the energy density stored in that scalar field is rather stable and it just dilutes like ordinary matter. Okay, so now we have a picture for how the energy density in this scalar field evolves. So at early times, rho is just, we just, at early times the field isn't rolling, we just have this result here, and we know that the field isn't changing. So at early times the energy density stored in this field is just constant. And then, when the Hubble parameter becomes comparable to ma, then what happens is that rho starts to dilute. As 1 over a cubed. So this is effectively a field that behaves like dark energy early on, and then it starts behaving like matter. So, that's the simple version of this story. The more complicated version is the present day Accin abundance. So to do this more carefully, again, you do a numerical evolution of this equation. You take into account carefully how the actual mass of the Accin evolved. I've treated this like a completely fixed parameter, but if there's some high-scale physics that is determining the whole potential, you know, there are higher order terms in this potential, and the mass can evolve as well. Depending on whether you're above or below the QCD scale, that can affect the physics if you're really talking about the QCD Accin. So if you take this all into account carefully, then what you get as an estimate from this cosmological production for the Accin is that the late time density goes something like this is to the 1, basically. So one thing here, why have I chosen to write this as theta naught divided by FA? Well, if you recall the range of our potential, the range of the potential that we wrote down originally was, if I can find my note, we said that the potential had minima to m pi. Or in terms of our new field, in terms of our classical field, that theta over Fa equals to m pi. So we can think of this ratio as being an angle. This is a dimensionless angle. And we know that if we're in the region around the minimum of the potential such that we're going to roll towards 0, then basically theta has to be between minus pi and pi. It has to be in that valley surrounding 0. So this is called the misalignment angle. This is an initial condition. It just tells you how far off was your axion from being at the minimum already in the early universe. So, okay, so this tells us a couple of things. First is that if we want, is that this angle can't be much larger than 1. I mean, maybe it can be 3. So this is an upper limit as a function of Fa on how much the axions can comprise of the dark matter. So this tells us that if we want, so if axions are 100% of the dark matter, then then this mass scale Fa has to be greater than this value. It can be if it's smaller than this value, then no matter how, I mean, theta just can't go to arbitrarily large values. It's an angle. It's constrained. So it could be, Fa could be much higher than this scale. You could have a situation where, you know, Fa was 10 to the 16 GeV or whatever, and theta squared gave you the 5 orders of magnitude that you need to get the right relic density, because theta could potentially be very small. But this tells you, again, that if you want axions to be 100% of cold dark matter, there's some fairly high scale physics involved. Okay. Now, you can say, okay, what does that correspond to in terms of the axion mass? And it's less than about 0.1 millieV. So this is consistent with our previous picture. If we want the axion to be cold dark matter, it needs to be lighter than about, it needs to be lighter than about 10 to the minus 3, 10 to the minus 4 EV, if this is the QCD axion that we're talking about. Now, and just qualitatively, the way that you can think about this relationship is that as Fa gets higher and higher, that corresponds to the axion mass being smaller and smaller. That means that you're frozen for longer times in the early universe, so this dilution starts later. So if you have a smaller mass, if you have a larger Fa, you end up with more relic density left because you just haven't had as much time to dilute the relic density with this 1 over A cubed scaling. So there are two, well, okay, so maybe I'll pause here before I say the next thing I'm going to say and just ask if there are questions about this, because I realize I just talked for a long time. Yep. Yes, so, well, good. Okay, yeah, so this statement that rho actually goes like a to the minus 3 will, I mean, this will hold in both radiation and matter-dominated epochs. Yeah, so if you, so you can work out what temperature this corresponds to broadly. So if it's in the matter-dominated epoch, then so you've got an M Planck in here, so if you're talking about like 0.1 milli, so yeah, so M Planck is 10 to the 19 GeV, so that's 10 to the 28 EV, and temperature of matter radiation equality is about 1 eV. So long as your MA is greater than about 10 to the minus 28 eV, this crossover is going to happen in the radiation-dominated epoch. If you're talking about the QCD axion, if you play with parameters for axion-like particles, then maybe you can change that. But yeah, so I think this is generally assumed to happen during radiation domination for this reason. And we know that if we want it to be dark matter, the mass would then not be 10 to the minus 28 eV, because then the wavelength is larger than the size of our galaxy. Okay, so there was a fair bit of algebra, but key points are just scalar fields can behave just like ordinary non-relativistic cold matter. The particular cosmology in this case is just that you have some initial condition, the density is frozen at that initial condition for a while, but then eventually it starts to oscillate in the potential, and while it's oscillating in the potential, its energy density has this matter-like behavior. And the QCD axion, this pushes you into this particular range of cold, thermally decoupled, light, dark matter. So you might ask, well, hang on, I mean, can't we do a little bit better than this? I've said this is an upper limit, but isn't there a naturalness argument here that theta, sure, it can take any value, but its ranges from minus pi to pi. So wouldn't you expect it to be an order 1 number? Well, there are really two situations. There are two possible situations here that people talk about. So situation 1 is that, situation 1 is that suppose whatever physics set this initial condition, whatever physics placed that axion at that position in the potential, suppose that happened after inflation. So if the scale of the physics producing the axions is at Fa, that would mean that the scale in inflation is much larger than Fa. Well, then we know that after inflation, the part of the cosmos that we can see today, back then consisted of tons of different causally disconnected patches, right? So in the CMB, we see photons from patches that back at redshift 1000 were all causally disconnected from each other. When we measure the dark matter density, we're measuring it over many, many patches that right after inflation were not in causal contact with each other at all. So if during that period, after inflation, when all these regions were disconnected from each other, you would expect them all to have different values of this angle theta. And by the CMB epoch, when we ask what is the dark matter density, we should really be averaging over all these ensembles. So in this case, you actually would expect this average value of theta squared to be an order 1 number if this whole range is randomly populated. So then that actually points you to a specific value of Fa around this 5 times 10 to the 11 GeV, 10 to the 12 GeV case. But the other possibility is that this happened before inflation. So this picture is inflation happened, the cosmos was a whole bunch of different little patches. So our volume that we see today is sampling a whole bunch of different patches with different values of theta. But the other possibility is that this happened before, or if theta was set before inflation, then before inflation, there would have been these many different patches with different values of theta, but only one of these patches then got inflated by inflation to be our observable universe today, and so then we would expect theta to have the same value everywhere. And then potentially our universe could have a very small value of theta. And there's been some work on trying to understand, could you justify this from an anthropic standpoint? Would all the other parts of parameter space where we had either way more or way less Accin dark matter just not be very hospitable places for life? In something like this case, you can actually, there are domain walls, but there can be domain walls between regions with different values of theta, and that can actually also produce a lot of axions. Numerically calculating the abundance of axions from this process is a hard problem. I know a few people who are actively working on it. But if decay of domain walls forming axions is an important mechanism, then this number will not be exactly right. So you have some room for slop there. So these are the two sort of general divisions of, so in axion parameter space, generally this misalignment angle is treated as a free parameter. But if you're finding yourself in a regime where you want this theta parameter to be extremely small so that the scale can be very large, then that may push you into this second category where you're positing that this initial condition was actually set before inflation. Any questions about that? People okay with this? So the main point of this is partly to say something about axions, but also just to give you an example of how you can have ultralight, and basically an ultralight scalar field, very small mass scale, generated by very high scale physics, which doesn't talk to the standard model, which barely talks to the standard model at all, and certainly wasn't ever in thermal contact with it, and that can give you the same gravitational behavior as having a bunch of 100 GeV stable SUSY superpartners floating around the universe. Everything that we know is at present consistent with both of those possibilities. Okay, do you guys want to just take a 5-minute break since we've been talking for about an hour, and then when you come back, then, yeah, so just take a 5-minute break. We will reconvene and I will talk about how you actually look for dark matter. Okay, welcome back. So, having talked about how you might get the dark matter relic density right, where we've seen naturally generated by thermal freeze-out or set by some initial condition in the early universe, let's now talk about, okay, if any of these ideas were right, how would we actually go about testing them, besides the gravitational probes that we talked about earlier? So, I'm going to start out by talking about the case that we just looked at, where what you're trying to understand is searches for the axion. Okay, so I will also note that there's a good review on this by Peter Graham and co. from 2016. And there's also, yeah, so if you take a look at this, this will give you a reasonable overview of axion searches, although there will be some that people have come up with in the last year or so. So, I told you earlier that we expected the axion to have a coupling which looked like, which looked something like when I put in the numbers. Okay, so like this is the coupling to the standard model that we know about. Now, if the axion exists, it could also potentially couple through the same kind of CP violating operator to the photons. So what people often test for is a term of the form of a coupling between the axion and the electromagnetic field. Now, the exact size of this term is somewhat model dependent, but it's reasonably generically expected. So this G, we would expect it just parametrically to have the same sort of structure as the couplings that we've talked about previously. The axion coupling in the standard model goes as 1 over the high scale FA. But the details of exactly how this couples it, there are a couple of standard cases called the, let's see if I can remember the names offhand. Yeah, so the DFSZ axion has couplings to photons, gluons, leptons, and quark. The KFSZ axion only talks to the photons and gluons. So there are a few different sort of general classes of models that people constrain. But often you'll see constraints which are just in the parameter space of the axion mass versus this coupling to photons. Because if this coupling to photons is there, then another way to write this term is just as the E field dotted with the B field in terms of the classical fields. And what this means is that in the presence of a magnetic field, axions can convert into photons and vice versa. So we have a diagram which could look something like this. The axion could decay into photons. We can also have this axion-photon interconversion diagram facilitated by an ambient B field. So. Okay, so what implications does that have? Well, there's a whole host of possibilities. So one is that if you have a region that is opaque to photons, some photons might be able to get through anyway because they can turn into axions and then turn back into photons. So you can have like photon, axion, photon conversion. So this could be like a literal wall in the lab, or it could be a region of the universe that we think should be approximately opaque to photons, because photons scattering on gas clouds or scattering on the ambient radiation field should just be fully absorbed in that region. But in fact, we see photons from that region. So that's one possibility, one possible observational signature of axion conversion. Another possibility is, well, if there's this axion field pervading all space, we have, since if it's the dark matter, then if you have an ambient B field, those dark matter axions could potentially convert into photons in your detector. So this could be in terms of you create photons apparently out of nowhere, or equivalently, you induce EM fields. If you're talking about the QCD axion, its variations, its oscillations can induce nuclear EDMs. This is the idea of the Casper experiment. Some of these I'm not going to talk about in detail. I'm just going to point you to the reference. They could, in the early universe, the effects of the QCD axion could potentially change the neutron-proton mass splitting, which can affect the nucleosynthesis of elements. That's an example there. So, so these are, so you can both have these interconversion effects with photons and other nifty experimental effects of the axion. This is not a complete list. If we focus on these two cases where we're looking at photon axion interconversion as our main detection channel, then there's quite a number of both lab experiments and astrophysical observations that you can potentially do to get a handle on it. So if we look at photon axion conversion, where I also mean this broadly to mean axions inducing electromagnetic fields and so on, then in astrophysics and cosmology, then you can enhance the cooling of stars. If you have a star that is, photons would just be absorbed within it, but the axions can get out, then that can potentially be constrained. We can see how fast stars are cooling. That will tell us if a lot of those photons are converting into axions and getting out. We can look at, as I said, there could be regions of the universe that the photons can't easily pass through. So you could see photons from higher redshifts than you thought was possible. And there have actually been a couple of claims of seeing photons from sources that are so early in the universe that you would have thought those photons would all be absorbed by the time that they got to us, particularly at very high energies, because sufficiently high energy photons can pair produce on the interstellar radiation field, and that tends to be a pretty inefficient process, and not many of them make their way to us. So there have been some claims from the Fermi Gamma Ray Space Telescope of seeing gamma rays from really high redshift sources that the universe should have been opaque to. However, that calculation does depend pretty sensitively on what you think the energy of the photons in the radiation field that you're scattering on is, because the criterion is that the high E photons are absorbed when the mean of their energy and the mean of the background light, the extragalactic background light, is greater than, or the root mean square of their energies is greater than the electron mass. That's the criteria for pair production to be allowed. So this depends sensitively on what you think the typical energies and the intensity of this extragalactic background light is. But that is a place where you could potentially get a detection in the future. So in the lab, where we have a little bit more control over the situation, there are what's called light shining through a wall experiments. If you want to convert cosmological axions into something that you can see, so the most famous experiment of this type is the Admx experiment. So they have a resonant B field, so they have a microwave resonant cavity, and they're basically scanning the resonant frequency of the cavity. And if the resonant frequency matches up with an axion mass, then they expect to get an enhancement of the power coming out of the cavity. So the picture here is, so in Admx, you have a resonant cavity. Let me say it a different way. So you have a, So you've got a resonant cavity with a strong B field. You want to measure the power output as you vary the frequency. And what they hope to see is that as they vary the frequency, their output power looks steady for a while, and then you get a peak at a frequency corresponding to the axion mass due to resonant conversion of dark matter axions passing through, converting into photons, and increasing the power out of the cavity. Now, sorry, let me give you a reference. So this experiment is getting pretty close to being able to probe the dark matter window for the QCD axion, but it's not quite there yet. But their current run is hoping to do better and start carving into that parameter space. You don't need to use, so you also have an experiment that I personally like, but I'm a little bit biased because a lot of my friends are involved in it. It's the experiment with the best acronym called Abracadabra, for which I refer you to their paper, which also explains what the acronym actually stands for. So what they're looking for is setting up a large toroidal magnet and saying that as the axions go through, it will induce a very small effective current in the magnet, in the toroid, which causes a B field at the center of the toroid at a point where all the standard model B fields you would expect to cancel out. So. Again, they have impose a strong B field. They get the dark matter. They want the dark matter axions to convert into E fields and make a small current in their ring, and that produces an induced B field. There's the Admx experiment. This field is strong in acronyms. So what they're looking at is saying that if you've got different dielectric materials, then you can look for axion-photon conversion at the interfaces. So all of these experiments are basically probing the same thing, which is this vertex. You don't even need to do this in the lab. You can look for axion-photon conversion in the magnetic field of astrophysical objects, such as the sun. And so the CAST is the current experiment, and the EAXO experiment is the next-gen experiment. Is use the B field of the sun to do your conversions to these solar haloscopes, where you look for the effects of axion-photon conversion around our nearest star. So where does this... So I'm not going to go through how these experiments work in detail because we just don't have time this week, but and these papers will explain it better than I could anyway. But where do we stand at the end of all this? What do the current limits look like? So if we look at this coupling, so this is a dimensionful coupling. We expect it to scale like 1 over FA. And we look at the axion mass in the EV scale. So we can start looking up at like 1 EV, although this would correspond to a thermal axion if it was actually the dark matter. 10 to the minus 3 EV, this is the boundary between hot and cold dark matter for axions. How far will I go? Okay, so if we've got something like the QCD axion, we expect there to be a characteristic band on this plot that is set by the relationship between MA and FA that we just wrote down. So let's just identify that band first. Okay. So this is the approximate band that, the approximate band that I just talked about goes from like 10 to the minus 12 here to at 1 eV goes like 10 to the minus 9. So we want at a milli eV, we want this to correspond to about 10 to the minus 12, to about 10 to the 12 GeV scales. That's what we talked about as the band for the QCD axion. So there's something like this, which if you're talking about the QCD axion or something that has a similar mass FA relationship, this is roughly where you'd want to be. And depending on the misalignment angle, the regime in which you can potentially get the dark matter density right is down here. So where do the various experiment? But you could have particles that are not the QCD axion, but a similar light, cold, scalar fields propagating in a potential which is pretty close to quadratic around its minimum. That's not a strong criterion. That could be called dark matter in just the same way. So on this plot, coupling scales, if I've copied this correctly, the solar axion experiments are pretty good at ruling out fairly big couplings, so fairly large scales. So this region up here is largely excluded pretty independently of mass by the CAST experiment. And the IAXO forecasts, if you can trust that IAXO paper which I cited, will push these down somewhat, sort of down into this regime. If you want a better version of this paper, the Abracadabra version, a better version of this figure that is not like my sketch, the Abracadabra paper has an actual version with numbers, which is, you know, what was up to date as of early 2016. Now, ADMX, I said that they're sort of starting to probe the cold dark matter QCD axion region. So far, the Admx constraints. So Admx, you remember, they're scanning the frequency to try to match the mass. So if they scan only a small range of frequencies, they can only rule out a fairly small range of masses. So the early versions of Admx have sort of ruled out several bands somewhere in this ballpark. But the hope is the forecast for Admx is that they can start carving down into this region. So they would be probing the QCD angle with a relatively large misalignment angle. So a scale where theta is order 1. Now, so this is so if you're happy with your misalignment angle, if you're sure that the solution to dark matter is definitely the QCD axion, not something like it, and you're sure that the misalignment angle should be order 1, maybe this happened after inflation, you should be keeping an eye out for the results from ADMX in the next couple of years, as they're going to carve into that parameter space. If you want to look further out in these regions of parameter space at these low mass and low coupling region, Abracadabra claims to be able, well, Abracadabra doesn't actually have any results yet, but they claim to have sensitivity to a region that is sort of down here and upwards. So this is the Abracadabra forecast. So with their toroidal apparatus, they can potentially probe this low mass, relatively stronger couplings than you would expect from the QCD axion regime. So that is, as far as I know, where we currently stand on the broad landscape of searches for axions, ideas for looking for axions. If you have another idea, this is a pretty fertile field at the moment, as you can see from the fact that a number of these papers, these are first ideas for experiments in just the last couple of years. So this is a region where, if you can come up with good ways to test parts of this parameter space, there's potentially a lot to be done. Any questions? Okay. So today ended up being basically 100% axions, and I didn't get to talk about direct detection of thermal dark matter. So the remaining 2 lectures then are going to be pretty much 100% WIMPs and the thermal regime. Something that I'm probably not going to be able to get to, so I'll just mention it now, is the idea of searches for particles which are not dark matter, but which are light and could potentially talk to dark matter, could potentially also talk to the standard model weakly. So these are dark photons and related objects. This has some overlap with the Accin searches if what you're talking about is light particles that are weakly coupled to the standard model. So I won't go into much detail on this, but there's a recent report from the US called the US Cosmic Visions. This is self-interested. I am a co-author. But if you just Google US Cosmic Visions, you will find the report. It has a lot of information on ideas for ways to search for Accin-like dark matter, and also to search for light particles that have some small couplings with the standard model. So then what I'm going to focus on in the next two lectures is direct detection and indirect detection of dark matter in the thermal window that we talked about last time. So we'll talk about direct detection, we'll talk about how the classic WIMP experiments like Xenon and CDMS work and why it's hard for them to probe light dark matter below the GeV scale. We can talk a little bit about ideas, well, it will be a very little bit, mostly just point you to references, about there's a big current effort to try to understand ways to probe lighter dark matter particles that are still in the thermal window. So not these cold scalar field type of dark matter, but dark matter that you can still think of it as a particle, but it's lighter than a nucleus. You'll see tomorrow why that's hard to study. And then I'll talk about today, and on Friday, I'll talk about my particular interest, which is what you can learn, what you can try to learn about dark matter from looking at astrophysical and cosmological data, the signals that you might expect from dark matter annihilation or decay, where they would show up, how you would look for them. Okay, thanks very much. See you tomorrow.